Hello, everyone. Force and impulse. We have talked about momentum in collisions, and every time if there is no external force, if the interaction among the object themselves there, then the momentum is conserved. But now we look into more details, how momentum actually changes, and but of course, this is due to the forces that make the velocity change, and velocity will have the input to the momentum. Therefore, forces actually make velocity changes and in turn make momentum changes. And so now we introduce here another quantity called impulse, and actually force impulse. So here, force and applied to an object for a certain period of time, usually very short, and like this tennis paddle, and apply a force and make it accelerate. But the force may be different, very short time, and the force times the time, it will give you, we define as the impulse. The impulse obviously is a vector because the force is a vector, so force times time. So why do we want this quantity? Because these quantities are directly related to momentum change. So remember, impulse, force times t, relate to momentum change. So we want this because many cases down here, if you look at the force just applied is not constant. It's not constant. So if you want a detailed force acting, how the acceleration occurs, and that's very complicated. But mathematically, it's solvable. But what we are really interested in is the average force. Therefore, we have a momentum impulse theorem. So the average force times the time give you the impulse. We can derive that is like it equal to the momentum change. Once again, impulse, force multiplied time, because the force changes the velocity, that equals momentum change. So usually that apply to very short time, but although it applicable to any duration. So force times delta t is the impulse, and impulse is equal to the momentum change. All right, we will do some exercise later on. Car moved in the same direction along the frictionless air track, each acted upon by the same constant force for a time interval, which means the impulse is the same. Now, we are asked to answer the question, which of the following statements is true? First, A, each car has the same change in momentum. So now, the change in momentum. So we just talked about the momentum and impulse theorem. Force times time, that's impulse, equals the change in momentum. So this is the same for both. Therefore, change is the same. So the first statement is true. So A is true. And the second statement, car 1 has greater change in momentum. Okay. Greater change in momentum. So then they have the same mass, but that's not true because the same impulse. Car 2, yeah, of course, is wrong because they have the same mass, same direction, and they have different mass. The change in momentum depends on the inertial velocities. No, that's not true either. So only A is true. So this is just directly apply the momentum impulse theorem. You have the same impulse and same momentum change. The second question, and similar to above situation, 6C11. For the situation described in the previous question, which car experienced greater change in kinetic energy? Now we recall the kinetic energy is half mv squares. Both speed will change. A, each car has the same kinetic energy. B, car 1 has car 2 has positive greater, and D is impossible to tell without knowing its velocities. So intuitively we answer this question. So if you think about this half, okay, mv1 squared, okay, and the other one is twice as much, half m2 v2 squared. Okay, and so if you apply a force, okay, impulse, and the velocity will change, but so then the change in different directions. But now see if you impulse it this way, okay, and this one for the one will be reduced, so the velocity square will be reduced. But if the other one is accelerating, so if the other one already, so I with 2, so the second one is this one, this way. So if you have the same impulse this way, and the velocity will be v2, absolute value will be actually going up, and vice versa. So the velocity, even though the impulse of momentum change is the same, the velocity squared really depends on which way originally is. Okay, without knowing that, you really don't know how the kinetic energy changes. So think about the velocity absolute value squared. Okay, and depending on what the initial velocity is, could be going up, could be going down. So, but the kinetic energy change will depend on the initial velocity. So then the answer is D. Okay, it's impossible to tell without knowing the initial velocities. And this second question put next to the previous question to make the concept clear. Then that's why we need to define both the momentum and kinetic energy, both related to velocity and mass. But kinetic energy will relate to the energy transfer, and momentum will only relate to the power, the force, and applied in each direction. But momentum is a vector, but the energy is a scalar. So the kinetic energy change could be going up, could be going down, could be both going up, could be this one going up, the other one going down, or that one going up, and vice versa, depending on the direction and relative to velocity, or it's deaccelerating or accelerating, and so on. So the correct answer is D. So our choice is D for the previous question. To back up the answer with mathematics, so that let's derive the exact result and see how the answer will depend on the initial velocities. So the impact is the same, impulse is the same. So now here we have same impulse, but then momentum changes same, then we can derive then the velocity change of the smaller one is twice as much as the bigger one, but depend on positive or negative on the direction, but absolute value wise, and smaller also have a change of the bigger one. Okay, that's expected because bigger one is more clumsy. So now the kinetic energy change, we just fall back to this original definition of a kinetic energy. So half mv squared for the first one is this, b plus delta v squared and minus that. And the same is for the second one, but then this mass is twice. And if you would substitute this relation to this and figure out this, we can find out which one is actually bigger. So usually to find out which change is bigger, you do the subtraction between these two. So delta E2 times delta E1, then you put all this mass, expand the squares, and then do that. And then, of course, if you want to know the details, we will have notes here. If you click the notes, I will have detail notes here, but probably you guys can more intimidated by the mathematics, but the result I read in here. So the change, we want to know whether it's positive or negative. So that's how you compare which one is change is bigger. For example, 2 change is bigger than 1, it's positive, which means this second one has more change. If that's negative, this one has a negative change. So that is calculated by substituting all this into this relation, and I get this, right? So pretty symmetric. So mass is always positive, 2 times V2 times delta V1 and minus the other delta V2, and that's V1. So realize these two terms are very similar. So but this one has V1, that one has V2, so delta V2. And then there's always a negative term, delta V2 squared. Therefore, if you say, well, which one has bigger kinetic energy change, which has bigger change because of the same impulse, and it really depends on which one is big. So which one is positive, which one is negative, all this. So whether this term is negative, say situation. Okay, V2 is very large, positive, and then positive change, and then that is very small, and these are very small, and they will change with positive. Okay, because bigger velocity, a bigger change. On the other hand, if V1 is very large, positive, and then this will be a negative change. So that will be small. So now, in a special case, if they have the same velocity, okay, remember, assumption is the one is bigger, the one is small. If they have the same situation, so this situation, same velocity in the same direction, or same direction, and if you plug in this, so if V1 is the same as V2, so these two first term will cancel. Only thing left is the last term, so it's negative, which means, and the second one will change less. Okay, the second one will change less. The bigger one will change less. So that same speed, okay, if the same speed, bigger one has less kinetic energy change. That is the thing to take home with. You have an impulse, a force on it. Now you want to sit in a bigger car. So that's big, its kinetic energy, it changes less, okay, than the small one if they have the same speed. Of course, if a big speed, of course, change more. Less speed, change less. So they're all different situations. And even either direction, if accelerating or that way or this way, deaccelerating, if they have the same speed, the bigger one have less kinetic energy change. So in general, so this is already extension, but I think the extension is interesting. So that's formally answer this question with mathematics. So it depends on velocities, but how? This is how it depends on the velocities. How it depends on initial velocities. Hello, everyone. Force and impulse. We have talked about momentum in collisions, and every time if there is no external force, if the interaction among the object themselves there, then the momentum is conserved. But now we look into more details, how momentum actually changes, and but of course, this is due to the forces that make the velocity change, and velocity will have the input to the momentum. Therefore, forces actually make velocity changes, and in turn make momentum changes. And so now we introduce here another quantity called impulse, and actually force impulse. So here, force and applied to an object for a certain period of time, usually very short, and like this tennis paddle, and apply a force and make it accelerate. But the force may be different, very short time, and the force times the time, it will give you, we define as the impulse. The impulse obviously is a vector because the force is a vector, so force times time. So why do we want this quantity? Because these quantities are directly related to momentum change. So remember, impulse, force times t, relate to momentum change. So we want this because many cases down here, if you look at it, the force just applied is not constant. It's not constant. So if you want a detailed force acting, how the acceleration occurs, and that's very complicated. But mathematically, it's solvable. But what we are really interested in is the average force. Therefore, we have a momentum impulse theorem. So the average force times the time give you the impulse. We can derive that is like it equal to the momentum change. Once again, impulse, force multiplied time, because the force changes the velocity, that equals momentum change. So usually that apply to very short time, but although it applicable to any duration. So force times delta t is the impulse, and impulse is equal to the momentum change. All right, we will do some exercise later on. Okay, in class we also detoured and to review some math concept of areas and calculus. Okay, let's see if you want to calculate the areas. So if you have this area, one side 1 by 1, so square, and its area is 1 squared. And now if I ask you, without telling you how to calculate this one, you say, how many of these square can be put into this second big one? You will say, well, roughly 3 or 4. You're right. And then we are very good at that. And how about this big square? And in class, one student jumped in about 8. Yes, that's what I thought too. Now, what about this shape? Okay, just give a guess. And then you will say, well, maybe 5. So here's 1, here's another square, here's another square. And what about this shape with the parabola? Okay, what's the area underneath? And someone can accent, oh, it's a 2.3, maybe 2.5, I will not stop you. But if you say a 25, no. You can say what, 0.5 or 2, compared to this, that's 2.3, that's 5. And what about this sine curve? And that one is, I would say, this upper loop is 0.3 and the lower loop is also 0.3. That's a 0.3. Let me talk about these areas. Okay, and that is about 1, and that is, inside that circle is 0.05 compared to that one. So we're all pretty good at that. And we estimate the area of some shape. Okay, usually you make it into some rectangle, which can easily calculate and compare to something you can calculate. By comparing something you can calculate, then that's the way to guess or estimate. Or you can say we do an approximate calculation. So in calculus, it does the same thing, but just try to get these estimate accurate, exact. So you have to use calculus to get the curve of the function to do it. That's called integration. And integration means adding together. So that's it. So we calculate the impulse of the changing force or variable force, and we have to slice the time in different time intervals and pretend that each interval the force is constant. Then we have a time multiplied by the force, and time multiplied by another time interval by another force, and adding each of the impulses together, we get a total impulse. That's why we need to review this to get an idea. Now let's solve some problems with force and impulse. Okay, and exercise 5, solving problems. First problem, 6p8. An estimated force versus time curve for a baseball struck by a bat is shown in the figure. So this figure here. So now the thing's a little bit complicated. Now the force is not a constant. If it were a constant, you simply multiply this force by the area, then you will have the impulse. But the force is slow, going up linearly and going down approximately. That's the force. So a bat just struck a ball, and the force goes up and goes down. Very short time. So 1.5 milliseconds. So then, as we discussed in class, to compute this non-constant force or uneven force, all you have to do is estimate just pretend that they are constant at different small time interval and multiply them and adding these impulses up for different sections. So that's exactly the same idea as when you learn calculus. You calculate the area under an irregular shaped curve. You simply slice this into different columns or long, thin rectangles and get the area of each of these and add them up. And that process in calculus is called integration. But put integration on side for so far, but this idea is also very interesting in approximately calculating anything that area under a curve or estimate some impulse with a force that's not constant. And that's exactly what we are asked to do in this question. Basically, we try to get the area under the curve. So for this question, you will have this. You can estimate, and then you can do different ways. For example, for this triangle, you can think about how about, you will say, well, this rectangle here with the base 1 millisecond and a full head is similar to that. I would say, well, it's roughly this, okay, because I don't know how to calculate this one, okay, but that is the same. What is that? Pretend the force is this, but it go 1 milliseconds instead of 1.5. But so then that's easy. So 1 times 20,000. So estimate is about 20,000. So you would say, well, this is about the same. But then in this case, or you can calculate this small area. What is the impulse of this small square? And then it's like 0.5 times 5,000. And in that case, this one is 2,500. So this is a small square. And then using that to see how many square this rectangle roughly have, you say 1, count this, 2, 3, 4, 5, and a little more. So 5 times that is about 1,700. You just add this thing up. You can. Okay, in this particular case, we actually can calculate the area of this exactly. But as we know, to calculate the area of this triangle, and we know, okay, we learned in math and geometry. So the base times the height and divided by 2. So that's exactly what we want, but you just have to use the units. So base is 1.5 seconds and height is exactly given 18,000 Newton. So let's see what is the area of this triangle. That's actually the impulse. Now we have here the impulse. We try to estimate the area, or in this case, under the curve, under this shape. And in fact, in this case, we almost exactly know. So if you look at the graph, so this was the one. This distance is 1.5 milliseconds. Okay, and then this height actually is already given exactly. So it's 18. So base times height divided by 2. So this is base. Okay, but I only have a luxury in this particular case. In other case, I give it to you. You have to really estimate. So the height is this. So we try to get the area under the curve. Okay, so the height. So this 18. Okay, and then divided by 2. So multiply this and divide it by 2. So then let's work on here. So base is, so this, okay, the force is 18. That's actually the height. Okay, 18 newtons. Okay, but in fact, this is the exact calculation. The height multiplied with the height is 1.5. So you know where I get 1.5 from. 1.5 is from the graph. Okay, that's base. And that's milliseconds, 10 to the -3. So that's milliseconds. We talk about that, milli. Okay, and then seconds. So I use the standard units. So then that's pretty easy to find out. And that is actually 13 20,500. Okay, and the units is standard units, and times 10 to the third, 10 to the negative 3. So times 10 to the negative 3. Okay, Newton seconds. That's the impulse of the bat on a baseball. So that's the impulse. Why do we want the impulse is for? And we want the impulse to equal the momentum change of the ball. And also from here is sometimes you want to know the average force. So the average force is A. So we use the triangle. Or what would be the answer if you just use the square, use this rectangle? So okay, roughly this. So that triangle is roughly that. Okay, and that is 1 times 20,000. Okay, and so since we are asked to estimate, that is, if you do that, so it's like 20,000. So you just guess times 10 to the third. So because the bottom is 1 millisecond, this is a lot easier. Okay. In reality, if I want you to guess or estimate or approximate calculation, you can do anything that, as long as it's close, it counts as correct, because you're safe under the word estimated force, and so that's the impulse. So then now, but this is actually we get exact. If you get 20,000, which is 18,000, or you get 20,000 a little more because you said it's a little bit lower than that, you will say 18,000 or something less. So now let's take this. So now B. So the reason we want to calculate the impulse is we want to know the average force. Normally, so over here, average force, you can do the average force, not if it's not average force times T. So what is average force? Is also equal to the average force. Okay, and what you do that is actually you get average force because it's changing. The fact that nothing is really constant in real world. So then you can just do approximate calculation. So average force, sometimes strong, sometimes weak, but the average force, then say you know the impulse. So the impulse, you divide the T to the other side. So then you divide T to the other side. So therefore, the average force, so this is derived. So average force and equals the impulse we already know above, and divide by the T. So then you do the math. So 13500 divided by 1.5, both times 10 to the negative 1.5. Oh. So, well, a little bit messy, but you know what I'm trying to do. We'll divide this by that, then you get average force. So average force, what I get is 9,000 newtons. So usually you have to explain what the result means physically. Okay, 9,000 newtons, what does it mean? Okay, so the bat on average acting a force by 9,000 newton. How strong is 9,000 newton? So just compare to the weight of 1 kilogram object. So 1 kilogram will sense gravity of 9.8 newtons. Okay, so if you divide that, how many kilograms it feels like? If you really hit your hands, on average it feels like about 900. Okay, about 900 kilogram feeling. Okay, kilogram is not force units, with about 900 kilograms. So it feels like about 2,000 pounds. Okay, 2,000. So this is the answer. So this is the final answer for here. And that is the answer. Okay, and that works as well because since we are asked to estimate. Okay, here is another version of the first problem. Calculate the impulse. All you need to do is estimate the area under this triangle. Okay, there are multiple ways. You can just look at the square part, or just based on your own intuition or your common sense. So if it's 18,000 on the top or 0 on the bottom, and then on average it will be just 9,000. So later on, only just to verify this with more accurate mathematics calculation. So first, what is the impulse? So then this case we can calculate sort of exactly. So the base times height divided by 2, and the base here is 1.5 if you look at the chart, and then height is 18,000, and then you do the base times the height and divided by 2, that is 13,500 times 10 to the negative 3, because that is milliseconds. So basically force multiply with time. Okay, that's the impulse. But then the force is varying, okay, or is changing. Therefore, you need to do the area under this. All right. So, or in general, it's supposed to be an integration. So now the second question is, what's the average force? Okay, you get the impulse. From the impulse, you can get the average force. So based on definition, impulse is the average force multiplied divided by times the time interval. And to get that, you simply move this to the right, the other side of the equation, or this way, reverse the equation. Average force, the impulse divided by the time. So the number are there. So the impulse we already calculated from here, and then divided by the time, so 9,000 newtons. Well, it's basically just to verify what you see here, the average force. Okay, so average force means it's not 0, but it's not 18,000. Average is 9,000 in halfway. But if any special shape, you have to do this process and do the impulse divided by the time, and then you get 9,000 newtons. So that's the idea. Okay, chapter 6, problem 9. Okay, the second problem. Okay, a soccer player takes a corner kick, like he is doing right here, and lofting a stationary ball at 35 degrees above the horizon. Basically, it's a slanted angle. Say this is the soccer ball, it will boom like this to the, and 22.5 meters per second. If the soccer ball has the mass of 0.24 kilogram, the player force contact time is very short time. 5 times 10 to the negative 2 is like seconds. It's like a 50 milliseconds. And what we want to find is the momentum change. Of course, you kick, and then there's a force, and provide an impulse. Then the impulse directly equal to the momentum change. Force interact for some time, then the momentum change. What is momentum change? Basically, what's the momentum of the ball? Because it started from 0 in velocity. So x and y components of the soccer ball. And so now, how do you find the problem? First, what is the momentum change? Okay, and then that is 22 times that. That's the momentum. And then, then that's the magnitude of momentum, but we remember it is a vector. It's not in either direction. The first question is multiply these two numbers, get the momentum, and then decompose into components of the same momentum. All right. The solution is on the next page. And the second is question, once you have the momentum, the magnitude of average force, and then you go back to the magnitude again. And simply the momentum is the momentum change divided by the time, then you get the force. So let's have a new page to talk about this. Continue from previous page. They were solving the second problem, and the soccer corner kick, the force and momentum we calculated. Okay, and from mass times the speed, and that's the momentum. And actually that is the change because it starts from 0. Then So that's a momentum change. So that's the first question. And the second question is actually the first question is about the components. So that's pretty easy. That's nothing but trigonometry, realizing that the adjacent to the hypotenuse is none other than just cosine of 35 degrees. So to get the components, all you need to do is multiply the magnitude with the cosine. So magnitude is this number. Cosine 35 degrees is something like 0.82, and then you multiply them together. So that's the components. Remember, the components is always less than the actual magnitude. So it's like a stick, its shadow, its projection should always be shorter than the actual stick. So then the y components and this part and to this part, we call the opposite side to hypotenuse, and then the hypotenuse is our magnitude, and then that multiply this, and then you do the rest. How do you get it? So that is the components. And the second question we were asked, and if you have the sheet at home in your hand, so what is average force? Now we're sort of doing this backwards. We got the impulse, and which is 9.56, and that equal to the force times the time. Okay, force multiplied by the time interval. But the force was not a constant. In fact, it's like a triangle shape. But the average force, that equal to average force times that. Therefore, the average force is nothing but you divide the whole thing by the time, and then you get an average force of 191 newtons, and that is it. So just to get the idea, get a feel about how strong is this force. And imagine 1 kilogram is like 10 newtons, 9.8 newtons precisely. And then if you probably know how it feels like holding 1 kilogram in your hands, like 2 pounds. And then, so this is like, if you divide this by 10, so it's like 19 kilograms. It's like 40 pounds. So basically, the kick, the player, his foot will feel something like on average 40 pounds, okay, of kicking. So that's 191 newtons. It's about 40 pounds of force. All right. This actually ends this section or this chapter.